All right, let me do this one. It's a pretty involved problem. It's one of the harder ones. And one thing that makes it harder is that it is velocity with respect to position rather than velocity with respect to time. So let's see how to do that. We have a boat traveling along a straight line, and it's got a speed as shown on the graph versus position s. Construct the ST and the AS graphs. Also determine the time required for the boat to travel 400 meters when it starts at 0. So our given information is the graph. We also want to know or find. I'm not going to redraw the graph here because theirs is a lot neater for your understanding. So the find is ST graph and AS graph and the amount of time when S equals 400 meters. Part of our given is that S equals 0 when T equals 0. All right. Let's look at, we need to find the position curve and the acceleration curve. So I guess we'll start, we could go either one, but let's start off with position. And we have a change in the function here, so we need to look at this in 2 steps. So let's look at S up to 100 meters, between 0 and 100 meters. We know what's our relationship? We need to find the position with respect to time. And what we have is velocity and position. So our equation that relates those is V equals ds dt, right? We've got time, position, and velocity. So we can rearrange that because we want to find time. We want to get time by itself. So if we bring this out here, dt equals ds over v. We can rearrange those. And we know what velocity is. We have this function. So velocity equals square root of 4s, right? If we rearrange that equation. So we plug that in here. And square root of 4 is 2, so we can make this 2s to the 1/2, which equals 1/2 s to the negative 1/2 ds. All right, we can just pull both of those up on top. And now let's integrate both sides. Sorry, I have a lot of equal signs in here. Got carried away there a little bit. Integral of dt, we're going from 0, in this case, to t. Since we start at t equals 0, s equals 0. The integral of this is going to be s to the negative 1/2 plus 1. It's going to be s to the 1/2. And that's going to be it, I guess, because it'll be 2 over 2, s to the 1/2. And this one, we are evaluating from s equals 0. It's going to start at 0 to s. So therefore, we find out t equals s to the 1/2, right? We have t minus 0 on this side. Then we have s to the 1/2 minus 0 to the 1/2. So we can rearrange this and say our function between from 0 to 100, s equals t squared. Hey, that's pretty cool. And that is meters. So when s equals 100 meters, time equals what? Right? this is not very clear. So 1/2 power. So if s is 100, 1/2 square root of 100, sorry, is 10. So that's 10 seconds at s equals 100. Okay, we're making progress. Now let's go to the next section. From 100 to 400 meters, what's going on? Again, we have our relationship. We can use this one up here, where dt equals ds over v. We have a function for v over here, which is ds over 0.2 s. So now we're going to integrate both sides. We integrate this one, not from 0 this time, because we're starting at 10 seconds to t, and s goes from 100 meters to s. This is the integral of what is that? We can simplify this by making 1 over 2/10 is the same as 5 times s to the -1 power, right? ds. This is 100 to s. Okay, so when we integrate dt, we get t. So we have t minus 10 equals this integral. We can bring the 5 out, and the integral of 5 of s to the -1 is ln of s from 100 to s. We're going to find that the function of how t relates to s, which equals 5 outside of ln of s minus ln of 100. Remember, we can do that with natural logs. And so we have, let's simplify this, because this also equals, let's see, where am I going to put everything here? I'm going to bring this 5, divide everything by 5. So I get t over 5 minus 2. Now I'm going to simplify the ln's, which is ln of s over 100, because I can simplify when ln's are subtracted from ln's. I can put that as s over 100, ln of that whole thing, and rearrange this. We're going to take e to this power and e to this power to get rid of our natural log there. So I'm going to have e to the t over 5 minus 2 power, and that's going to equal, I got rid of my ln that way, so I have s over 100. Let's see, what else can I do here? I can simplify, just take the 100 over, so I can find out that s equals 100 e to the t-fifths minus 2. Now remember this operation again. We can take that of t over 5 divided by e squared. Because since those powers are subtracted, e to the power subtracted is the same as e to t over 5 divided by e to the 2. I know this is reviewing a lot of math here. Now we can calculate e to the e squared. We have the natural Euler's number here times itself times 100. So we can simplify s to be 13 0.53 times e to the t over 5 power. Okay, so that is a good number here. It's important. And now we can evaluate at s equals 400. Where are we? Well, we've got 400. We can take 400 divided by 13.53. That equals e to t over 5. We solve that. We find out t equals 16.93. Woo! All right, so now we can make our, I hope I don't run out of room here, position versus time function. We know that s equals 0 at time equals 0, and then we know at t equals 10 seconds, s is at 100, and at t equals 16.93, let's see, let's start here. At t equals 10, s equals 100. And then here, s equals 400. And what's going on between there? So this s equals a t squared function. As s goes along, t is going to get bigger faster. So it's going to start out kind of like, it's going to be a little bit curved. And then from here to here, the second point, it also has a curved shape, something. All right, so now we know where that boat is at any given time. It's a pretty powerful process here. And we can find the acceleration. So let's find acceleration from 0 to 100 meters. And this will be a little more straightforward. Okay, we have a relationship that we can use. Acceleration equals dv dt or v dv ds. Okay, now we know a function for v is up here. So, make sure I got everything in the screen here. So our velocity as a function of s is vs, and if we took the derivative of, sorry, v is actually square root of vs times dv ds. So if we took the derivative of square root of 4s over ds. All right, so let's work on that. We're going to take the velocity, start back over here, acceleration equals the velocity, which is square root of 4s, or we know square root of 4, we can simplify this a little bit, to s to the 1/2. That's our velocity function from up here, times the derivative of square root of 4s, which is the derivative. We can take the derivative, the square root of 4 is 2, so we can take the 2 out and get the derivative of s to the 1/2 ds. Now what's the derivative of s to the 1/2? Okay, so this equals 4s to the 1/2 times 1/2 s to the negative 1/2. Right, we're just taking the derivative of s to the 1/2. This is s, okay. So we simplify this down. Let's see. When we multiply, s to the 1/2 times s to the negative 1/2, what do we get? We add the exponents and we get s to the 0. So this comes out 4 times 1/2 times s to the 0, which equals 2 meters per second squared. Okay, that's great. And that's a constant. That's cool. So we found acceleration from s equals 0 to 100. Now let's find the acceleration from 100 to 400. Again, we're going to look at our function. We're going to have a equals v dv ds, which equals 0.2 s, because our velocity is from up here. Velocity equals 0.2 s, and dv ds, the derivative of that, is 0.2. Right? Derivative of 0.2s is, we just dropped the s, we have 0.2. This is a lot easier. We end up with 0.4. You know, it's really best not to use more than 2 equal sign in an expression. So that's pushing it right there. So acceleration equals 0.04 s, which equals 1/25th s, right? It's 4/100ths, which is 1/25th. So we found that one. So let's see if we can graph this. We need to graph A versus S. Okay, that's a little bit more straightforward maybe than A versus T, but we can work through that. It starts out S equals 100, S equals 400. And A starts out at 2 meters per second. It's constant. And then it goes, what does it do at s equals 100? This function, acceleration equals 4. Even though it's only 2 here, acceleration can change instantly. Velocity can't really. It's stuck to the mass, but acceleration can change instantly, just like this. As soon as I drop the pencil, acceleration is instantly 9.81 negative, but velocity is still 0. Now at s equals 400, acceleration equals 400 divided by 25 is going to be 16. And these are meters per second squared. Okay, so, and this is, what's the function look like? We have a equals 2 here, but the other one, a equals 1/25th s. So it's going to go up. It's going to get up to 16. My chart is not going to be to scale. So it's going to go straight because this function is a equals s over 25. Okay, so did we cover everything? We want to find out how much time is required for the boat to travel a distance of 400 meters. Yeah, we found that already. Time equals 16.9 seconds. And we have our 2 graphs.